All right, so here we go with problem number 106 from chapter 10. So it says, consider the arrangement of bulbs shown in the drawing. Each of the bulbs contains a gas at the pressure shown. What is the pressure of the system when all the stopcocks are opened, assuming that the temperature remains constant? And then we can neglect the volume from this little tubing in between. So these little valves right here are called stopcocks, and we're going to open them. And remember, a gas fills the shape of its container. So when I open all of these, this nitrogen is going to fill this container and this container. It's going to spread out to fill them all. And so its volume is going to go from 1 liter to 2.5. 1 plus 1 plus a half to 2.5 liters. So its volume is going to expand. Same thing with neon. It's going to go from 1 liter to 2.5. Hydrogen is going to go from 0.5 liters to 2.5 liters. And so we actually have 3 different problems here. One for nitrogen, one for neon, and one for hydrogen, because we want to know the final pressure of the whole system. And each one is going to have its partial pressure along with it. So the first point is to take the pressure and volume and temperature data from nitrogen and organize it. So here's the initial pressure of nitrogen, the initial volume of nitrogen, the final pressure of nitrogen, the final volume of nitrogen. Its temperature doesn't change, of course, but square this or box this and put +1 once you have it organized. The second point is for organizing the data for neon. So neon has initial and final conditions as well, where this is 800 torr for neon, 1 liter to start with, and then it expands to fill its container at 2.5 liters. We don't know the final pressure yet. Temperature, of course, doesn't change because it says temperature remains constant. The last one is hydrogen, and that one goes from 1/2 liter to 2.5 liters, so that has a larger change in volume. Starts at 532, goes to we don't know what. 3 points so far, 1 for each setup. Now for each one, it's a vice-president relationship. If the volume goes up, which for each thing it's going up, the pressure is going to go down. And so I need to multiply the pressure by a fraction to make it get smaller. And my fraction choices are 1 over 2.5 or 2.5 over 1, and I'm going to choose 1 over 2.5 because I want it to get smaller. So 265 times 1 over 2.5 is 106. Same thing for neon, except it's 800 times 1 over 2.5. Same thing for hydrogen, except it's 532 times 0.5 over 2.5, which gives us 106. Now, to find the total pressure, we need to add all these partial pressures together. So when you add all of them together, you get 532 torr total. This problem is worth 3 points. Put the number that you got correct out of 3. You're welcome to post up questions in the chat, or if you want to be real brave and unmute your microphone and ask a question, more than welcome to. This type of problem right here with the bulbs and opening them up, there's 2 of them at least on the test, and so it's one that I really wanted to go over in greater detail. The next one is number 75. Number 75 says, determine whether each of the following changes will increase, decrease, or not affect the rate with which gas molecules collide with the walls of its container. And in letter A it says increasing the volume of the container, and so I had a container that was this size, and then I said, okay, let's increase it to this size. So if you increase the volume right here, the molecules that were in this part of the container now can spread out to a much larger container, and therefore they will decrease in the number of collisions they will have with the side of the container because they're more spread out. They don't bump into each other as much anymore. That's worth 1 point for 75. B is increase, C is decrease. We're not going to correct those. Any questions, post them up in the chat. All right, the next one is number 61, and this is very similar to the first problem that we did, except this time we have 2 bulbs, and we open the stopcock right here, and then it asks about a bunch of the data that would occur after these 2 gases mix to fill the shape of their container. So I have initial final conditions here for the nitrogen, initial final conditions here for the oxygen, and then I have a final answer down here. And I'm not going to spend a lot of time on that one because I spent a bunch of time on one exactly like this just a little bit ago. All right, the next one is number 57. 57 is a tough one because this is a So a gas stoichiometry problem. To be able to do a gas stoichiometry problem, you first of all need to remember the steps for stoichiometry. Write a balanced equation, convert to moles, use the mole-to-mole fraction, and then convert to the asked for units. So let's go through 57 step by step. The metabolic oxidation of glucose in our bodies produces CO2, which is expelled from our lungs as a gas. And the balanced equation is done for us right here. So we're good on the balanced equation part. We don't need to do that. The second thing is we need to convert to moles. We're given 24.5 grams of glucose, and you can go from grams to moles. You're good at that. So 24.5, 1 mole, 180 grams. When you add up 6 C's, 12 H's, and 6 O's, that's worth 1 point. Highlight that, put it in parentheses, make sure you box that so I know that you got that right. Step number 3, mole-to-mole ratio should be a fraction that relates glucose to carbon dioxide. So you can see it's a 1 to 6 fraction that we're going to need. So for every 1 glucose, there's 6 CO2s, plus 1 for that relationship right there, 6 to 1 relationship. Make sure you got the units in there, box that, parenthesize that, put plus 1 on there. All right, the next step then, once we have our number of moles, is to convert to the asked for units. Well, the units that they're asking for is the volume of the CO2. So we need to convert to liters. Well, if we know the moles, we know the pressure, we know the temperature, now we can use PV equals nRT to find the volume right here. So solve perv for V, then V is equal to nRT divided by P. Here's the number of moles, the universal gas constant in atmospheres, the temperature, and the pressure in atmospheres. Box that in, put plus 1 for having this work. The answer is 21.4 liters. That's not worth a point, but having the work is worth a point. Now, if that was a tough problem for you, B is exactly the same. I'm not counting it for points today, but there's all the work for B. Turns out to be 40.7 liters, and you can go watch me do this problem on the work problem sets if you're still stuck on how to do it. But I know that there's a gas stoichiometry one like that on the test, and it's worth 10 to 15 points, and so it's definitely worth the time to remember the stoich steps and to know how to use perv here at the end. The next one is number 52. 52 says calculate the density of sulfur hexafluoride gas at 707 torr. So to find the density of a gas, you need to remember your density equation for a gas. And if you have one of these gas equation cheat sheets that you wrote down from class the other day, you can find density is equal to military police over rapid transit. So M is molar mass, P is pressure, R is the universal gas constant, and T is temperature. Military police over rapid transit. So here's my equation right here. I can pluck the pressure and the temperature right off of here. And since I know it's sulfur hexafluoride gas, which is SF6, I can add that up on the periodic table to get the molar mass. So it's 1 point for writing out the work right here. 146 for the molar mass, 707 for the pressure. This is the R value right here in torr. Make sure it's in torr. It's got to match this one. 294 is the Kelvin, and this is what you get for grams per liter. 1 point for that problem. Box in the work. That's the important part. Now letter B. B is almost exactly the same problem, just with asking you for a different variable. Here they're asking you for the molar mass. So they're looking for capital M now in letter B. And so you can still use density is equal to military police over rapid transit, but now you're solving for military. You're solving for M. Now, I didn't count this one as a point. You can go ahead and write down the work if you want, or you can go and watch me do that problem as well. But that's the second part to 52, where you have to manipulate the military police over rapid transit equation to find M. Next problem is number 48. And this one says, rank the following gases from least dense to most dense at 1 atmosphere of pressure. And so once again, you need the density is equal to military police over rapid transit equation. And you can see that density and molar mass are directly proportional to one another, meaning that if one goes up, the other one goes up. So if molar mass gets larger, the density gets larger because they're equal to each other. They're on top of the fraction over here. And so to find out which one is going to be the least dense and which one is the most dense, well, you have to find the molar mass. So you got to add up SO2 on the periodic table, HBr on the periodic table, CO2 on the periodic table. And the bigger the molar mass, the more dense it is. So when you rank them, CO2 is the least, hydrogen bromide gas, in this case, is the most dense, least to most. That's worth 1 point for having that ranking system. Highlight that, make sure that you understand how the relationship works between density and molar mass. All right, probably the toughest problem right now, number 43 is next. Toughest because it's long and there's lots of parts to it. Maybe the other ones are tougher, but anyway, this has got several parts to it. This one talks about chlorine gas in a municipal water supply, something we just talked about. It's also used in swimming pools. Suppose that the volume of a particular sample of chlorine gas is, and then here's our volume, our pressure, and our temperature. Our volume, our pressure, and our temperature. Notice I organized it right away. Then it says how many grams of chlorine are in the sample, and so if you want to find grams, one of the equations you can use is PV equals mass over molar mass times RT. If you don't know where I got that equation, remember on the gas law equation, you can find it right down here. PV equals right here. Mass over molar mass times RT. We want to find mass right here. So multiply both sides by M over RT to get them to cancel right here, and our equation ends up being M equals PVM over RT. Now we can take this data and you can plug it right into that equation, find the R value that is for torr, and if you forgot where the R values are, once again on your gas equation sheet, here's the R value for atmospheres, mummy hugs, kilopascals. Remember, mummy hugs and torr are the same thing. 1 point for having this work. Box that in, square that, star that, highlight that, put +1. Now letter B, C, and D, the next problem's tricky because you probably think, oh, these are all PV equals MRT, PV equals MMMRT, or PV equals NRT problems. And it turns out B, C, and D are not. They are all initial and final conditions problems. And so lots of times students get confused about, well, how do I tell if it's a P1 V1 over T1 equals P2 V2 over T2 problem, or if it's a PV equals NRT problem. My recommendation is to first organize your data like this for every single problem. Start with initial values of pressure, volume, temperature, and if you have another column here for number of moles or mass, that's fine. And as you go through reading the story problem, if you start to get final in volume, pressure, temperature, number of moles, then you know it's this type of problem. If you don't get any data about final or changes to those, well, then you know the only thing is I'm missing one variable, and now you have to use either POV equals MMMRT or PV equals NRT per unit. So anyway, I organized the data like this to start with, and I found out I have to find the final volume. This one's not worth a point, but it turns out to be 9.42 liters. The next one, I did the same thing, organized my data, and then I did it a little differently. I didn't plug it into the PV equals, or the P1 V1 over T1 equation. I said if temperature and volume are directly related, if volume goes up, then temperature's got to go up. So I multiplied by a ratio to make the temperature go up, 15 over 8. And temperature and pressure are directly related. If temperature goes down, if pressure goes down, temperature's got to go down. Remember the toilet paper relationship? So I multiplied by a fraction to make it get smaller. And so I ended up with 501K. Circle, square, star, box that. Put these in parentheses right here. Give yourself +1 for that problem. Here's the answer to letter D as well, in case you want to write it down and wanted to check yours if you haven't checked it already. Told you that was a tough one and a long one. 37 is the next one. This one is the number of molecules in a deep breath of air. So organize your data first. PeV equals nRT. We're looking for moles, and then once we get moles, we can find molecules. So solve for N. N is equal to POV divided by ERT. Put the P, the V, the R, and the T in there. Make sure T is in kelvins, and you end up with multiplying that answer by 6.02 times 10 to the 23rd, and you end up with 5.15 times 10 to the 22nd molecules. Box that, put +1 on there if you corrected that correctly. Letter B asks for the same type of thing in an adult blue whale, and this one ends up asking you for mass. So you have to end up converting to moles, and that ends up being converting from moles to grams, and that ends up being about 6.4 kilograms. That one is not worth a point. Now, there are a number of other ones in the textbook. This is 21. This is number 19. This is number 13, and this is number 1. And you can go and watch me do these if you're not sure how to do some of those, but we're not going to correct any more of those for credit. But what we are going to do is go to the gas laws practice worksheet, which looks like this. Or if you've never seen the paper version of it, it would be on here, and it's called the gas laws practice worksheet, and it looks like this. Okay, it has lots of gas laws practice problems. We're going to start from the back end, and we're going to do number 39 first. It says, does the density of gas increase or decrease or stay the same as the temperature of a gas increases? Justify your answer with a hypothetical mathematical equation. Okay, so we're looking at density and temperature and how they relate. Well, if you look at your gas laws cheat sheet on here again, you can find a relationship between density and temperature right down here in density equals military police over rapid transit. Transit, T stands for temperature, and density is right over here. And you math people are excited about this relationship because you can see that density and temperature are inversely related to one another. That means if the temperature goes down, the density goes up. Or if the temperature goes up, the density goes down. They're opposites of one another. Temperature goes up, density goes down. Temperature goes down, density goes up. Circle, square, star, box that relationship. Give yourself +1 for that. Just having this equation and noting that it is an inversely proportional relationship is absolutely fine. That's what we've got time for today. That is 13 points out of 13. Put your score, please, at the very top of the page. Note how many you got right. Remember, you're not scored on how many you got right. You're just scored on how well you scored your paper. So make sure you've got your things circled, squared, starred, or boxed. If you missed any of this, the video of this is going to go online probably in the next 15 minutes or so.